Okie dokie. So last time we introduced this notion of having some kind of dynamic memory management facility, which uses an area called the heap, which is separate from the stack. The heap is large, and we have a runtime that actually manages the heap. And I mentioned before that each process, and we haven't talked about what a process is yet, but if you just want to think of a process as my program and its execution context. So I'm running my program, and I have a heap available for that program to use for allocating larger chunks of memory. We had these two functions, malloc and free, where you could say, I want this amount of memory, and if it could say yes, if it says here's some memory, then it'll return a pointer to it, untyped, so we have to cast it to whatever we want to use it as. And when I'm done, I have to release it. So I have to manually deallocate things using this free function. And so obviously all kinds of challenges can ensue if you don't use this facility correctly. We also talked about arrays, where we have an array declaration, and you can compute the address of element I by multiplying the index I by the size of each element and then adding that to the starting address of the array. And we already can do this in C using pointer arithmetic. So notice that I have A, and then in square brackets I is equal to A plus I, A being an address and I being the index, and then dereferencing that, because that'll be a pointer. And adding I moves it forward I elements, not I bytes. So it's very important to understand the vagaries and the nuances of pointer arithmetic. Do you know why? Because you get to write an allocator in assignment 3. And you'll be doing a lot of pointer arithmetic. And so you can see that whatever the type of the pointer is, when I add or subtract from it, has a huge impact on how much I actually move. So types are very important when it comes to pointer arithmetic. So we introduced these ideas last time, and we were going to start exploring how to implement this function in IA32, vector add. And notice we take two pointers to int arrays. We're told their length in the argument, and then we're supposed to heap allocate a new array and compute the result into it, and then return the results array. And somebody else has to worry about releasing the memory. And this caveat is extremely important. If you try to type this code that we will write today into your Mac, it will not work. And the reason why is because the way that you call functions like malloc and the way that you expose functions like your vector add function is very different on the Mac than it is on Linux or on Windows. And so it's a little bit annoying. And if you want to see what the Mac does, I would recommend write this C code and then do what we had last time, GCC-S-O2, and see what it generates. And you'll notice that although some of the details are identical, some of the details are very different, and it's those differences that prevent us from being able to do this on just any platform. Okay, so first thing is we need to figure out how the stack is going to look when we're invoked. Obviously, we need to know about that. So using the cdecl calling convention, which argument gets pushed first? Length, right, good. I'm glad people are sort of memorizing what cdecl does. So length is pushed first, so it'll have the highest address on the stack. Then B is pushed second, and then A is pushed last, because we push the arguments in reverse order. Okay? So EBP plus offset locations, arguments are pushed last to first. So inside of our function, presuming that we are setting up a frame pointer, EBP, like usual, you probably will almost always do this. The way that I normally do it is I set up the frame pointer and then later remove it if it becomes clear that I don't need it, unless it's completely obvious from the very beginning that I won't need it. So you might as well just set it up. So that's why we have this stuff. So length B and A pushed by the caller. The call instruction is executed. That pushes the return address. And then when we enter our subroutine, the first thing we do is we say push EBP, move ESP into EBP. And that sets up the stack the way that we have it here. Okay? And so A is going to be stored at what? Well, it's pretty obvious. Just keep in mind we're on 32 bits. Or we're doing, even though we may be on a 64-bit machine, we're still doing 32-bit programming. So A is going to be at, each one of these values is 4 bytes, so 8 EBP. Okay. B is stored at 12 EBP, and length is stored at 16 EBP. Any questions? Okay, Cdecal is going to be your friend all term. If you don't know it very well, it is a cruel taskmaster, but otherwise it's your friend. Let's see, what else? So, given that this is the case, the first thing that I always like to do when I'm writing an assembly function is to put in all the stuff I know. And you can see that that involves a couple of things. First of all, I know what my function's called, so I put a label there, vector add, and then I write some comments saying where stuff is. Because when I write my assembly code, I'm going to have 8 EBP somewhere. I'm not going to have A, because unfortunately that's the level that we're at. And 12 EBP, and I'd like to have some lookup table at the top so that I, the human being, can easily understand what the assembly code is doing. So that's the first thing. Document, okay, I have my function call, or my function name, I have my arguments where they are, and then I have various placeholders saying what steps I need to go through. And some of these things will always be here. You can see that we have our common preamble where we push EBP and then move ESP into EBP. We have a to-do saying, well, any callee save registers I modify, I need to make sure I save them. I have stuff that the function does, so allocate space for the result with malloc, implement the vector sum loop. Those are obviously going to vary depending on the function I write. At the end, I restore the callee save registers I saved earlier on, and then I have my common postamble, if you will, or just the end of the thing, that I clean up the stack. So move EBP into ESP and then pop EBP in return. Okay? So you might as well always start here. Don't feel dumb writing out what you have to do, because the more that you define the answer, the easier it will be to write the rest of it. Like, I have no idea what callee save registers I need to save right now. So I'll worry about that later when I actually have some more information. Now we have to call malloc. Notice this is what the C code is. Result equals int star malloc length times size of int. So malloc also follows Cdecal, so I know exactly how to invoke it. I need to push length times 4. So remember that size of is a function that is evaluated at compile time. And we know just right off the bat the size of int is 4. So we can just say, well, we need to compute length times 4. That's pretty easy. We can just shift it left 2 bits. And on IA32, we can do that in one instruction, because shift left takes an argument that says how many bits to shift it. We call the malloc subroutine, and we know that the answer is going to be in EAX, because that's how Cdecal works. Now, what is our function going to return? Yeah, it's going to return something in EAX, but you'll notice that, well, we need to return the memory that is allocated by malloc, and since it comes back in EAX, why not just leave it in there? And we'll just, that way we're already set up to return our result. Yes?
Can length times 4 be calculated at compile time?
Length is not a constant at compile time. If you knew, for example, that you were calling vector add with 23 all the time, yeah. So so it's interesting because sometimes compilers are able to infer that, and at very aggressive optimization levels, they might in fact even do that. This is a pretty simple function, and it would not surprise me if compilers were able to optimize this. Just as a little aside, you guys had the fact function for assignment 2. I don't know if you realize this, but if you write a recursive factorial function and compile it, let's say that you write it in C, and you compile it at the appropriate compilation level, GCC will actually turn it into an iterative function. It will eliminate the recursion. So compilers are getting really good at optimizing slowly written code to be really fast. So, but at least in our situation, we don't have the guarantee that length will be constant. So we have to compute this in our assembly code to go ahead and handle this. Okay, let's see. What else do we have to think about? Yeah, so since we want to return the memory that malloc returns, we might as well just not touch the register that it's in, because we're already set up for the result. So this is the assembly code we would write for that. Now you'll notice I have ... here. That's the to-do. I don't know what I'm doing yet with the callee save registers and the preamble that we normally have, setting up the frame pointer. So we allocate space for the result with malloc. We move length into ECX. How easy is it to understand? 16 EBP, of course. It's obvious that that's length. So we have to use our little lookup table to say, oh yeah, 16 EBP is length, so I move that into ECX, shift it left 2 bits, now it's length times 4, push that onto the stack, now I can invoke malloc, and the answer will be in EAX. But I can't forget to clean up the stack because that's the caller's responsibility in cdecl. Now I could also do something like add 4 to ESP. Meh, who cares? Especially since this is ECX, and ECX is a caller save register, so we could trample it and not restore it, and it's the caller's problem if they wanted that value. Okay, so you'll notice various details like that. But this is the code for calling malloc in our simple example. Are there any questions about this code? Just as a little note, of course, as I mentioned before, the L on move L and the L on shoal and the L on push and pop, you can infer these from the assembly code, so you don't strictly have to write them, but it's a really nice thing to do just to make sure that everybody understands what in the world you're doing. Okay, blah, blah, blah. The next thing we have to do is implement this for loop. So you can see so far that we have implemented result equals int star, blah, blah, blah. We've done that part, and we know how our function is going to be invoked, but we really haven't done the rest. You can even say that we've implemented the line int star result and return result, because we already have our answer in EAX. We just have to figure out sort of the rest of it. So we need some loop variable for I, and although we could do this in the stack frame, we could have space allocated on the stack for that. That would be slow, so we'd prefer to use a register. And so I chose ESI. Why? I don't know why. That's just the one I chose. Okay? If you happen to like some other register better, like EDI or whatever, then choose that one. But anyway, we can compare that directly to length, because we can have, in our compare instructions, we can't have both of them be memory locations, but one of them can be, so we'll just compare it directly to 16 EBP. That wouldn't be ideal. If we were doing this in an optimal way, then we would probably want to move length into another register so that we could do very fast comparisons, but we don't really care at this point. So we need to access element I of arrays in B, A and B. And so we know that we have this scaled indexed memory addressing mechanism on IA32 that's really powerful. And in fact, we can store the start of the array in one register and the index in another register, and then we can specify the element size as long as the element size is 1, 2, or 4, or 8 bytes. So we actually can do everything we need with this scaled indexed memory addressing. So you can see now that we're getting a sense of what we need to store in registers. We need to have our loop variable in a register, we need A and B in a register, and hey, look, we already have result in a register. It's already in EAX. So we have, fortunately, enough registers to do this. You can see here that we move 8 EBP, or A, into EBX. So EBX will be the start of A, ECX will be the start of B, and we zero out ESI. And we had several different ways we could do that, but I'm doing it just by moving 0 into it. I guess variety is the spice of life. And then we need to do the for loop itself. So we have all the variables that we need now for assembly code. And we recall from last lecture that a for loop is just a while loop with some initialization code and some update code. And the while loop is just a do loop with an if statement in front of it. So again, when you're writing this kind of code, you can start with the C code and go through this series of steps, translating it into assembly code so that you don't have to just make this giant leap. We don't want to do that, although you can see I do that on the slide. But in general, you would want to do this as an iterative process so that it's much easier to do. So we've already peeled off the first test. You'll notice here, let's just look at the comments for now. First for test is I greater than or equal to length. If it is, we jump over the loop entirely. Otherwise, we do our loop body. It says here EDX is A sub I. EDX then has B sub I added into it, and then we store that into R sub I. And then we do our update code, which is I++. So we go ahead and increment ESI. That one at least is easy enough to look at right now. And then at the end we say, well, it's a do while loop, so is I still less than length? If not, fall through the loop. Otherwise, we jump back up to the start. Okay? So conceptually, we just applied the same series of steps that we had in our last lecture and then translated this into assembly code using our registers. Okay? So We will ignore the compares for a moment because they kind of warrant special attention, but our vector add loop is pretty straightforward. EBX is the start of A, ESI is our index, I, and our elements are 4 bytes. So we have EBX, ESI 4 in parentheses. Move that into EDX. We add ECX, ESI 4 into EDX. So we just pull B sub I out and add it into EDX. And then we store that value into the appropriate location of our result. So EAX, ESI 4. You guys see how easy it is to do array indexing in IA32? It's awesome. I mean, if you're doing this on a RISC processor, you really will be groaning and grumbling a little bit because you have to do all these calculations. What's the address I want to do? And then you have to use the load instruction to pull that into a register. This is much simpler. It's kind of very straightforward once you get used to the instructions and the addressing mechanisms. So just look at the code and see exactly what it's doing. Okay, then we have inc ESI, and then we compare it to the length again. Remember, the length was 16 EBP. And if we're still small enough, we're not up to length yet, we just go back and jump up to VAdd. Okay? Now, is there any questions about this code, except for the compare parts, because we'll talk about those next. Again, it's pretty straightforward. So the reason why I don't like compares is that they don't play well with the AT&T syntax. This is the one thing I don't find intuitive when it comes to the AT&T syntax. And just as a caveat or fair disclosure or whatever, I took 5X when I was an undergrad. I was a 5X TA. I know Intel syntax. I still like AT&T syntax more. Whatever that's worth. But comparisons are the one thing that kind of suck. Okay? So we have these lines, compare 16 EBP ESI, compare 16 EBP ESI. And you'll notice that I say here, is I greater than or equal to length? Is I less than length in my comments? Well, you'll notice that when I do the compare, I reverse the arguments. And that is for a reason. If I wrote them out the way that I have them in my comparison, then it flips the sense of the operation that I'm performing. Or it flips the direction, I should say, because it doesn't really flip the sense. Okay, so compare source 2, source 1 sets the flags as if you did source 1 minus source 2. So like I have here in the second to last bullet, when you're doing some comparison operation between A and B, it's really most intuitive if you compare B to A, because then your conditional jump operation or your conditional whatever operation will match whatever's in your pseudocode or your C code or whatever it is you're trying to implement. Okay? So that's why I say here, I want to compare I to length, but I say compare length to I, and that way I can say, well, if I is greater than or equal to length, jump over the loop entirely. And same thing at the bottom. Well, I want to compare I to length, so I say compare length to I, and if I is still less than the length, jump back up to the start of the loop. So that's my preference. You can certainly do this the other way around, where you say, well, I'm actually going to say compl ESI 16 EBP. But then, good luck figuring out, I guess that would be JL, right? Because you're saying is the length less than I. Yeah, see, that already is like making my head hurt. So I'm like, forget it. I'll just switch the compare arguments and then it's all fine. Okay, make sense? So just keep that in mind. This is going to become an important slide, I'm sure, on assignments 2 and 3 and probably a midterm coming to you so that you can understand how to do comparisons easily. Now, the last thing we need to think about is what call save registers have we changed? And if we went back and looked at the implementation, remember we used EAX, call or save, we don't care. EBX for A, that's call save, so we have to save and restore EBX. We used ECX for B, well that's call or save, so we don't care. We used EDX to compute into, that's also call or save. And then we used ESI for our loop variable, I. So we have to save EBX and ESI, and we have to pop ESI and then EBX, because remember it's last in, first out. Okay? So the call save registers, now that we have everything else, is easy to fill in. Okay? So that's the whole implementation. You obviously is spread over multiple slides, because who wants to look at a whole slide full of tiny assembly code? If you do, then you've come to the right class. But, the whole thing is now implemented, and we can actually use this code now in a C program. So like I say here, we save the assembly code into vector add.s. And the one little detail that we left out is if we want to be able to call vector add from other code in other files, we need to add this .global directive to say, hey, vector add is something that you can call. Okay, .global, as I mentioned before, makes this symbol visible to other functions. I should be more careful. It actually makes it visible to other source files, other translation units, other object files is really the most accurate answer, but we haven't gotten there yet, so we won't use that most accurate answer. But anyway, this is the minimal thing you have to do. You might want to do the P to align. You really don't have to get it to work. Our code, none of our code really in CS24 needs to be obscenely fast. So we don't really care about alignment too much at this point. Okay, so we assemble it using AS. We say I want to generate the object file vector add.o, and we give it our assembly code. And because our slideware is perfect, we get no errors. We just get a happy vector add.o file. And you can actually add debugging information as well if you need to step into it. That'll become very helpful in assignment 3 as well. So here's a test program. And you can see that I have vector add. I have a, what do we call it? I forget what we call it. We have a declaration of what the function is. That has a term, but I don't remember what it's called offhand. I don't know why I blanked on that. But anyway, this is basically to allow C code to know how to call our vector add function. Because the compiler can't just look at the assembly code and know exactly what to do. So we have to tell everybody, yeah, vector add takes 3 arguments. The first 2 arguments are int stars. The third argument is an int length, and it returns an int star. So now other C code knows what code to generate to call vector add. We generate a couple of vectors. You can see we just statically allocate them because we're really lazy. We don't want to call malloc for them. We have an int star for the results. And we go ahead and add the 2 vectors together, which means we should get 7, 9, 11, 13, 15 in our output. And then we just have a simple for loop that goes through and prints out the contents of the result. Then we free the result because, hey, the caller allocated it. We ought to be responsible and clean it up. And then we return 0 to indicate the program is happy. Okay? So a very straightforward program. And again, we can compile this using gcc-c. That'll generate an object file for va-main.c called va-main.o. And then we can link these things together using the GCC compiler driver again. Va-main.o, vector add.o, and we generate an output file called vadd. And when we run it, it magically prints out the right answers because it's slideware and there's never any bugs in slideware. Okay? So this is pretty awesome. This is how you would go about creating your own assembly function and obviously implementing it with all the details of translating C or pseudocode into assembly code and then calling it from another C function. Okay? Any questions at all about this? Pretty neat. You already have examples of this in assignment 2, I know, and so I know that this is a little bit late in coming, but this gives you the ideas. Okay, so yeah, we had scaled index memory accessing, or memory addressing. This is really nice. This makes our life so simple, and also, some of you, if you've already done the LEA problem on the assignment, you'll see, well, you can use LEA to compute addresses to use for memory addressing as well, so that now we can do arrays of structs and so forth. We actually are very rich in what we can do, so it's pretty neat. We can call C runtime functions or C standard library functions from assembly code now. We just need to follow cdecl, respecting the fact that we're now the caller instead of the callee. And we're able to return a heap allocated chunk of memory to the caller. So now we can return something that's much larger than 1 register. And it also doesn't live on the stack, so it doesn't go away when our function returns. I know, probably some of you have seen the problem of a function returning a pointer to a piece of memory on that function's stack frame. So you're returning a pointer to the caller that immediately is invalid, and hilarity ensues. Okay? I've had friends who've written code like that, and I kind of want to knock them on the head. The memory needs to last longer than the function invocation. So that's what the heap allows us to do. So that was all nice. We had this other function we talked about as well. finding primes. And we're going to explore this just a little bit. We're not going to go all the way down to assembly code for this one. But we had this function. We give it an argument n, and it returns some kind of collection of all the prime numbers. And the size of the result depends on the input. And we also kind of need to build up the result as we go. And so maybe instead of an array, since we don't know how big of an array to allocate, and we might need to reallocate it depending on if our array of results fills up, let's just make it simpler. Maybe we'll use a singly linked list or something like that instead. So hopefully you've all seen this data structure before. Int list, we have a value that's in this node, and we have a pointer to the next node. And you'll notice that the pointers type is the same as our struct that it's declared in. And if you ever wondered, well, how in the world does the compiler figure out this anyway? Because you're inside of int list's declaration, but then you have an int list reference to it. The thing to keep in mind is, yeah, the compiler may not know what size int list is yet, but it does know what size a pointer is. So it's just happy because it's like, okay, you have a reference to some type called int list, but I'm inside of int list declaration, so I'm okay. It's a pointer, it's 4 bytes, I can go on, I can deal with this. Okay? And then we have our function find primes. We've now updated it to return a list instead of just an array. So here would be possibly the most simple algorithm one could ever come up with. It is very naive, it's very slow. I is 2 to n. So n is the value that we're looking at. If it's prime, add it to the list. How much easier could you get? I mean, you could probably have all kinds of ways of optimizing this code. You could put optimizations in as prime. You could change what numbers you actually look at. And like I say, it is simple to implement, except possibly the list part. The easy way to deal with lists is to, oftentimes you'll have your pointer to the start of the list. That one is kind of a given because you have to know where it starts. If you don't keep track of that, you can't return the entire list. But oftentimes it's also helpful to keep track of the last node you created because that's the one you want to tack the next node onto. If you didn't keep track of this last node pointer, you'd always have to go and walk through the list to put it on the end. Or you'd have to put it on the beginning, and people are kind of weirded out when the answers come back in reverse. So we'll just go ahead and keep track of the last node. And we'll use malloc. That part is easy. We already know how to do that. So like it says here, to create and append new list node. So we have int list star new. And we use that to hold a pointer to the new element that we allocate. And we say new's value is I. New's next pointer is null, because we don't know if there's going to be a next one. And then we say if the last node pointer that we've created is not null, then we know there's an element, so we just tack the new node onto last by setting last arrow next to be the new one. Otherwise, we know that this is the first node in our list, so we need to set result to new. And then finally, we say the last node we created is the one we just created. Now, I'm not asking you to do this, but do you think conceptually you could probably figure out how to do all of this stuff in assembly code? It's not horrendous, right? We know how to call malloc. Size of int list is going to be a constant at this point, so maybe it's 8 bytes. Actually, that's probably a good guess. It is 8 bytes. Okay, so malloc 8, I can call that. I can store that into some register. I can access elements based on that. I would do like, let's say that it comes back in EAX. Well, you could do 4 EAX and 8 EAX to set these values. You could update these other things based on that. If last was like EBX, and you could do 4 EBX to set new, last arrow next, and so forth. So you can see how to do this. It's pretty straightforward. You could probably figure out how to encode all of this. But here's the point. There is no way to create such a data structure existing purely on the stack. Remember, the stack has a very limited usage pattern. I push stuff on it, and I pop stuff off of it. Okay? And the reason why I'm bringing this out is because we had these two reasons why we like the heap, and why sometimes the heap is preferable to the stack. Okay? Sometimes the size of the results is going to depend on the values of the inputs, so I need to allocate different amounts of memory. Secondly, I need results to be able to live beyond the lifetime of a procedure call. Okay, then it needs to be on the heap. And now we have a third reason. I can create more interesting data structures. I can create trees and linked lists and hash tables and skip lists. And oh, my heart pitter-patters with excitement. Now I can create these new and exciting data structures. Okay? So these are all reasons why it's nice to have a heap facility. We can start doing some very powerful things with it. Okay? Any questions on this? The next thing I want to talk about is how these things are laid out. It's funny because last lecture, some people were asking, well, what would this value be, or where would this value live? And these were good questions to ask. It just wasn't yet time to talk about it. Operating systems impose certain patterns or constraints or conventions, if you will, as to how programs are laid out in memory. It is a very operating system specific thing. So the OS picks an approach, and then everybody has to follow it because, hey, the OS is the one that's running. And like I say, memory regions are devoted to stack, heap, instructions, constants, global variables, and so forth. They always start at a particular location. They tend to be in the same order so that you generally can find things in the same place. It makes it very straightforward to understand what's going on inside your program. Okay, like I say here, these regions may vary in size, though. Instruction data. Well, not every program is the same size, so some programs will have many instructions to load. Our vector add was very simple, so we probably have no more than a few hundred instructions to load. Some programs may not have global variables. I hope not. They usually don't. That's actually not true. There's a few things that are global that are just set up by the OS for you. And then, the compiler will determine many of these details at compile time, and then other things depend on the program behavior. If I had my little find primes thing and print them out, and I said I want to find the first 100 primes, I should say all the first primes that are less than 100, I would generate a certain number of values. But then I could run the exact same program and say, now I want to find all the primes under 1,000,000. And the answer would be very different. My heap usage would be much larger the second time than it would be for the first time. So here is, I say a common memory layout. It turns out to be the 32-bit Linux memory layout, so that's why we expose you to it, so that you can become familiar with it. But you can see that we start with program text at the, and I should also say address 0 is at the bottom, and the address goes up. I guess that's convention in this class. So program text comes first, then initialized data, stuff with values that you specify at compile time. Uninitialized data, stuff that you're like, whatever, I don't care. Typically it's initialized to 0 by the OS. And then the memory heap starts after that and grows upward. And way above that is the stack. And that grows downward. And that way, the ideal is that they meet as late as possible. Because if they meet, your program has a problem. Okay, so program text, I already talked about this. Stack is at the top. The heap is above the fixed size program data so that we have as much space as possible to assign to the heap. And this is all for a specific reason. Okay. Now typically you'll have the kernel appearing in there somewhere. We haven't talked about what is a kernel, why does it have to be in my program, get out, all of that kind of stuff. We haven't really gotten there yet. But this is the general program layout that you have. These variable size memory areas have a couple of different limits. The heap, for example, I may start out with like a 4 megabyte heap, and then I may never get to that point, at which point the operating system is fine. We'll just stay within 4 megabytes, but maybe I say, well, I actually need 50 megabytes. And so the operating system will extend the size of the heap for the program. So that's a soft limit. I'm able to move it. But at some point, it'll hit a hard limit or a hard stop where it's like, if you go beyond this point, it means you have a problem. Or maybe you reach the point where the address space is full and you just don't have any more memory to allocate. And so when you get to that point, the OS will say, sorry, program, you're misbehaving, and it'll go ahead and abort it. The textbook mentions this value that is kind of older, kind of anachronistic, called break. And that is the point where the memory heap ends. And there's a special function sbreak that you can call, which is a kernel function that will allow you to set the heap size. And so this is what the malloc implementation would generally use if it runs out of heap space. It's like, hey OS, this program is really a memory hog and I need more space. So it'll call sbreak to say, give me more heap. A lot of other systems, though, OS 10 in particular, uses get R limit and set R limit. The R stands for resource, so it's get resource limit and set resource limit, and that basically is the more modern way of setting the breakpoint on the memory heap. Where does the memory heap actually end? Okay? So the stack itself we saw is easy to manage. And this memory region plus stack pointer. The heap is a lot more complicated. The stack, we can generate code to manage it automatically. And how easy is that, right? We can push stuff, pop stuff, really easy. The compiler takes care of all of that. But the heap is really complicated because the heap has no idea what order memory blocks are going to be requested. It doesn't know what sizes will be requested. You can imagine that there's a lot of bookkeeping that goes on in the heap implementation itself. Like I say here, the data structures are necessarily complicated. Now, it turns out that they're not so complicated that we can't implement them in the Intro Computing Systems class. And there's a way of implementing a memory heap that's not horrible. And so that's what the Assignment 3's suggested approach is, to have a pretty straightforward, simple approach, because we don't want you to get burdened down with all kinds of insane bugs to track down and so forth. But that heap memory is managed by this software component called a heap allocator. That's what the malloc and free calls go and interact with, the heap allocator. And like it says here, it receives allocation requests. It tries to satisfy them as hard as it can. But it has limitations, so sometimes it has to say, sorry, I can't allocate this memory for you. And then when you say free, it's got to record that the memory is now available for other things. Heap allocators fall into two main categories. One is explicit allocators, and by explicit, it means that you have to free things yourself. Okay, so you have to explicitly release memory, or perhaps the explicit means that you use a lot of naughty words when you try to debug your code if you're using an explicit allocator. But anyway, you have to manually release memory. Implicit allocators only require you to allocate memory, and they take care of the problem of releasing it. So implicit allocators use garbage collection to identify memory that is no longer in use. Okay? So Python, Java, Scheme, and many other languages use implicit allocators. And some languages actually allow you to use either explicit allocation or implicit allocation. And you can certainly use an implicit allocator with C++ as well, or C. There's actually a GC library that you can use in C and C++. It's not perfect. We'll talk about it more in the future. But you can even use implicit allocation in C and C++. We're going to start looking at explicit allocators, because you do get to write one in Assignment 3. I was mentioning before, we don't know what order requests are going to come in. We don't know what interleaving of allocate and free operations will occur. Will we get only allocates and then only frees? Or we have allocates and frees and allocates and frees? We have no idea what sizes will be allocated. And sometimes this leads to situations where even though we have the total amount of memory that's required to satisfy the request, we don't have a single block, a single contiguous block large enough to satisfy the request. So really small heaps, 6 kilobytes. This would be like if you're using a computer from the 70s or the 80s. 6 kilobytes total space. And our first allocation request is for 1 kilobyte. The second one is for 1 kilobyte. Third one is for 2 kilobytes. And then the last one is for 1 kilobyte. Then the program frees B, which was 1 kilobyte. So now we have some space left. And then if another allocation request comes in for 2 kilobytes, are we able to satisfy this request? Yeah, we have fragmentation. We have a problem. Now, a good question to ask would be, well, why can't I slide C and D around? Expense is actually not the problem. Because you can actually do this in a way that's very inexpensive. Yeah, the problem is that when we have explicit allocators, they typically are used in languages with pointers. And when you have a language with pointers, a lot of times we'll have pointers used in these data structures or these memory chunks, and the allocator has no idea where all the pointers are. So if it slides C up by 1 kilobyte, how in the world is it going to know what all pointers are affected by this? You guys should remember this from just the find primes example that I gave you. Malloc little chunk of memory, and one of the values in that memory was a pointer to some other chunk of memory. So if I start sliding stuff around, I have to go and update pointers. I don't want to deal with that. Okay? So that's why we're not allowed to coalesce. Okay, that's what we actually call it when we smush stuff together. Okay? I say here it's available, but it's not contiguous. So we call this fragmentation, and there's several different kinds of fragmentation. But this issue is very serious. And what you can do is you can have systems that run for a long time, and as the time goes on, if the allocator is not able to avoid fragmentation, the system may start suffering from low memory, even though the total memory available is actually perfectly sufficient to continue running. There was actually an article on Reddit about this about 2 or 3 weeks ago about some aerospace company that had to deal with this kind of problem, and they created a special allocator to deal with it. Okay? So it's kind of an interesting thing that people totally run into this all the time. Okay, we can't modify a memory block once it's in use. Okay, so yeah, we can't modify allocated blocks. This is basically all the stuff that I was just talking about. The allocator can't find and update these pointers. Okay? So really, all the allocator is allowed to do is manipulate the stuff that's free. And even that is risky because sometimes programs are dumb and they free memory and then they go and try to use it again. So sometimes you'll see situations where you free memory and then a program crashes because it tried to access something and the allocator actually assumed the program was telling the truth when it said, I'm actually really done with this, even though the program decided later it wanted to try to use it again anyway. Okay. So here's another sequence of allocations where allocate 1 kilobyte 3 times. So we have A, B, and C are all 1 kilobyte. D is 2 kilobytes. And then I free C and then free B. Okay. So now I have these two 1 kilobyte chunks next to each other that are free. And I try to allocate 2 kilobytes. Well, now we have another interesting situation. What if our allocator isn't intelligent enough to realize that these two chunks of memory are next to each other? Yeah, it will still think that we don't have enough memory. So we actually call this false fragmentation because we really do have the memory to satisfy the request, but the allocator isn't smart enough to realize that. Okay? Some students, homework 3 allocators, suffer from false fragmentation. You know, when you go through this implementation, I always say keep it simple, stupid. Go ahead and start with the simple stuff. Like you can implement an allocator and not coalesce, and it'll work okay. You can even implement an allocator and not implement the freeing part, and it'll work okay until it runs out of memory. So you can do this, and you can say, okay, let me get this part working, and then I'll add a little complexity, and then get the next part working, and then you add a little complexity and get the last part working. So you can stage this implementation. You don't have to do it all at once. And students who do it all at once frequently are up very late Wednesday night and then need an extension. So just be aware of that when you're implementing your allocator. Okay, so like I say here, coalescing also needs to be fast. We can't have a situation where we have to hunt all over the place just to figure out that these two blocks are actually adjacent and free. So there's all kinds of really fascinating strategies to deal with this. Okay, so those are some of the issues that we have to deal with. We have like 8 minutes left. That's plenty of time. The last thing to talk about is data alignment. Some of you are probably already familiar with this notion of data alignment, but this is also a very important thing that allocators have to think about. Because so far, we've talked about memory as if it's just a big array of bytes, and each byte in that array has its own address. And so if I want the byte at address 17 hex, I just go and look in my array, and there it is. I just pull out the value. Ooh, it's 91. And then I say, well, I want to add 4 to it, and now it's 95, and I put it back into box 17. Wow, life is so simple. But the processor is not an 8-bit processor, right? In our case, we're talking about 32 bits, but most of us are using 64-bit machines. Maybe you've worked with GPU programming, and that's 128 bits sometimes. Or even back in the old days of when x86 first came into existence, the 8086 processor had a bus width of 16 bits. And what that means is that the processor, when it interacts with memory, is always reading and writing chunks of data that are not 8 bits wide, but are in fact 32 bits wide or whatever the word size is. Okay? So we have this picture, but this picture turns out to be an abstraction as well. That's the point of what we're saying here. This box, or this diagram with all these individually addressable bytes is actually not the full picture. So the memory is constructed also to provide 32 bits at a time, 16 bits at a time, or 64 bits at a time. So what we end up with is a reality that's more like this picture. A 32-bit word size, so each one of those boxes now holds 4 bytes. And the addresses are slightly different as well. You'll notice that, well, since I access, let's ignore that right now, but each box has its own address, just as before. So the first box containing 4 bytes is at address 0. The second box is address 1, with another 4 bytes, and so forth. So you see addressable cells hold 4 bytes. And it really isn't possible to just access only the third byte, or only the second byte at a time. You kind of have to access the whole 4 bytes. That first box isn't quite lined up. That's like, my obsessive compulsiveness is coming up. Yeah, that's bothering me. Okay, but anyway, the way that you deal with this is that the memory has a way of saying, yes, I need to access this word at address 2, but since the word contains 4 bytes, I really only want to work with the first byte, or the second byte, or the first 2 bytes. So it has a way of masking out which bytes you actually care about interacting with. So like you see here, the processor is presenting an abstraction. The entire system is, because the memory is also using the larger word size, but the processor is giving an abstraction that you can actually access individual bytes, even though the CPU is using this larger word size to interact with the memory. Okay, is everybody with me? That's the first part. So this is what the picture kind of really looks like. We have 2 things going on at the same time. And as a programmer at this level, it's good to be aware that this is what's going on. So we have these addresses inside the boxes, which are the byte addresses. And then we have the addresses to the left of the boxes, which are the memory cell addresses. And each cell holds 4 bytes. And the addresses to the left of each cell, those are the addresses the processor has to send out. But our programs use the addresses inside the boxes. So I access address 19 hexadecimal or 1E hexadecimal. That's what my program does, and then the processor turns that into address 6 or 7 to access the corresponding cell. Okay? So let's say that I want to write a value FF to the byte address 06. So my program says I'm accessing address 6, and I want to set it to be FF. And what happens is the processor turns around and says, well, that corresponds to memory cell address 1. Okay. Shift it right 2 bits. That gives us our memory cell address. And then we also, the processor has to say, well, since that's the third byte in that memory cell, I need to set up the mask so that bytes at address 4 and 5 and 7 aren't dealt with. I only want to actually modify address 6. So this is all what the processor is doing for us behind the scenes. Okay, does that make sense? Complicated, huh? I'm really glad I don't have to think about this. Except sometimes you do. So what would happen if you tried to do an access that was not aligned with the actual size of our memory cells? What's the processor have to do? Yeah, I can't do it in one read. Because I'm telling you, all this stuff is hardwired. The bus comes out this size, and the processor just gets those bits. It can't like magically rewire itself to do this. It has to do 2 reads. Okay. So then it goes ahead and assembles these things into a single word. So like it says here, read the memory cell at address 1. Notice 01. I just need the last byte, but I guess I got to get it. So it goes ahead and reads that cell, pulls out the last byte, and then it reads the second cell and keeps the first 3 bytes and assembles those things together in the processor into our 4-byte value. Okay? So you can see that some memory accesses are slower than others, which sucks, right, if you want to write a fast program. Now, that all aside, this is if we're lucky. Because we may also have a processor that simply does not play ball when we try to do these kinds of accesses. And you may be familiar with this if you've done like Lec07, I hope. But for example, PowerPC. Macs used to use PowerPC processors. They could do this with 32 bits, but if you wanted to do 64 bits, they're like, it's got to be word aligned or I'm crashing your freaking program. And it actually wouldn't crash the program. What it would do is the processor would say, nope, 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 I'm not doing that. And so in software, this access would be emulated. How much slower is that even than having the processor take care of it for us? So, I'm sorry?
I said a lot.
Yeah, a lot is the right answer. Just take the OS class and you'll see how many other things are sometimes emulated in software. And it's like, oh, the humanity. So anyway, yeah, so like I said here, since this, word-spanning access complicates the processor logic, some processors just say, you know what, I'm not even dealing with this. You've got to deal with that kind of stuff in software, or just don't do it. Okay? So anyway, like I said here, the program tries to perform such an access, the CPU generates a fault, and then the operating system can step in and emulate the behavior with software, but then that's even slower. So it's much better if the program just doesn't do these non-aligned access. Okay? IA32 is fine. Like I said, CISC architecture, like 2,000-page manual, it's badass. It can do this kind of stuff. This is no big deal. It's just slow. Okay? But like I say here, the memory allocator does need to be aware of these kinds of alignment issues. So the compiler is clever, and it goes in and it positions things on specific boundaries. You probably noticed that the whole P2 align thing, that's part of the reason why. But we saw that on instructions, and we didn't talk about why yet, but it turns out that it's also going to align data in the same way so that these things can be easy to access or fast to access. So it says here on a 32-bit system, we might position values so that they only are at addresses that start at multiples of 4. And that way we know that we'll be okay with these alignment things. Okay, like I said here, it is typically not the case that you have to think about that. I bet nobody thought about this in CS1. Unless you were thinking about other classes while you were implementing your boring CS101. Okay? But this is a real thing, and you think about it at this level because it does have a huge impact on the performance of your system. Or maybe the system doesn't even support it. Okay? And the allocators are the same, where they actually will hand out chunks of memory that are word aligned. Or even like, I think that Linux hands out things on 16-byte boundaries. So it actually goes even more than this. Okay, so like I said, you have an allocator that keeps regions aligned on 8-byte boundaries. Let's say you're on a 64-bit system and you'd like to be friendly. And a request for 53 bytes comes in. I don't know who would ask for that. But let's say you're allocating a string, and the string happened to be 52 bytes, and we have a null terminator on the end. So the allocator says, well, 53 is nice, but what I'll do is give you 56 bytes. And you notice that the address is aligned on an 8-byte boundary, so the bottom 3 bits are all 0. Which is interesting because we can now use those bits for something else. Okay? We'll talk about that more next time. Right? So what we'll do more next time is we'll continue exploring how allocators work and various strategies for dealing with fragmentation. And then we'll talk about the data structures that underlie these things as well. So we'll see you on Friday.